To begin with, I wasn't sure if everybody picked up on this when I sent out when the gravitational wave news came out, and I sent out that little article by Dr. Rizzi and a little message that wasn't sure everybody picked up on the understanding that he worked on the LIGO experiment for many years. He was one of the early people involved in the development of the instrumentation, which is why he lives in Louisiana, because one of the LIGO detectors is in Louisiana. So I thought that was pretty cool. It's pretty exciting to be part of something like that. Okay, so today we're going to study dipoles, electric and magnetic dipoles. And so first we're just looking at the field around a dipole, the fields around a dipole, phi and E for an electric dipole, and A and B for a magnetic dipole. And so you're actually able pretty easily to derive the phi and E field around an electric dipole. That's actually pretty easy to do. And so I step you through that. And again, we're looking at, remember, we're doing a far field, looking at the far field around the dipole. So the electric dipole is formed by a pair of bodies with opposite charge separated by a distance d. And so we want to construct a vector P, which is the product of the charge and the distance between the charges, and is in the direction of going from negative to plus. And let's call that vector D. So that goes from the negative charge to the plus charge. And that's the electric dipole moment. So you can increase the dipole moment by either by increasing the charge or increasing the separation. And so we can generate the field around. The easiest way is to do the electrostatic field. And we're looking for the far field. So there's a point over here at some distance, at some r relative to the center of the dipole. And we want r to be much greater than d, the separation between them. This will be the far field. And so we use the general approach of Taylor series, and I step you through that here, and you should be able to find then that phi as a function of the position then is qz d over r cubed, where z is the z component. I'm specifying the z axis here along the direction of the dipole. Written in terms of p, this is then p dot r over r cubed, or in terms of r hat, dividing out a distance from the numerator and the denominator would be p dot r over r squared. So the phi has then a definite dependence on the angle, and also phi will go like r to the minus 2 in the far field. Okay, so that's a very compact way of writing phi. And then from phi you can find the gradient. The negative gradient gives the electric field. And in Cartesian form you can write it out, but this next step is to show that you can write this in a very compact form, which involves p again, p dot r hat minus p over r cubed. Okay, and let's examine what that field looks like. Are there any questions about how we got that? I'll refer you for the details to the solution, but if you have any questions, we can go over that now. So let's note that the electric field strength goes like r to the minus 3. So the dipole field drops off like 1 over r cubed. Of course, the monopole field drops off like 1 over r squared. But the direction of the dipole field is much more interesting than the direction of the monopole field. The monopole field, of course, just points radially outward or inward. The dipole field, of course, has a richer structure to it. So again, this is far field. So we have this tiny little dipole. We're really far away from it. Here's the dipole moment like this. Okay. Now the electric field, let's suppose we look in a region where r is parallel to p, and that would be, for example, straight up or so let's look at straight up. So we're up here in this region. R is parallel to P. Going back to this form here, if R hat is parallel to P, then P dot R hat will still be in P, in the same direction. So in other words, P dot R hat is equal to P, and then P r hat is back to P again. So we have then that the electric field in this region goes like 2P, or is equal, in fact, 2P over r cubed. So the electric field points upward, like that. And if we're down below, that r is anti-parallel to P, so you're down below, you get the same thing. The electric field is also upward, 2P over r cubed, like that. So the electric field points upward here and here. If, on the other hand, you're in the plane of the equator of the dipole, if you imagine drawing a line here through the center of the dipole and coming out like that, that defines a plane here. It's perpendicular to the dipole. Anywhere in that plane, r is perpendicular to P. And then P dot r hat, of course, is 0. And so there, the electric field now is just that second term, which is negative P over r cubed. Okay, again, it falls off like 1 over r cubed, but now it's pointing in the opposite direction to the dipole, so the electric field is this way, out here. And it's half the strength of what it was, even at the same distance. And if you fill out the rest of the field, of course, what you see is you get this characteristic field for dipole. Looks like this. Looks like that. It's strong and negative like this. And we're looking at far field solution. We're not getting up close to the dipole, so I don't want to sketch it too close to the dipole. But it comes out, the pole, it comes out the north pole, comes out the positive pole, goes in the negative pole, and is opposite, is downward in the plane of the dipole. And, okay, so that's what the electric dipole, far field electric dipole looks like. Okay, so now let's consider the magnetic dipole. The magnetic dipole, you don't have some of the tools to calculate the A field, for example. We're going to go through the same approach here. I want to sketch the magnetic dipole field for you. He goes through this at the end of chapter 3. He derives the magnetic dipole field from a current loop. And remember, we've said that a current loop generates a far field that is very similar to a natural magnet with the north and south like this. If you get far away from the loop or far away from the magnet, the natural magnet, then the field looks the same. And so he shows you mathematically how to find the A field out here at any point at some distance here. And that field depends on the magnetic dipole strength. So we define M, which is the product of the current going through the loop and the area of the loop. And the area vector points upward from the circle such that the current flows counterclockwise around this if you're looking down on the circle. And that plays the role of the magnetic dipole moment. Just like there's an electric dipole moment, this is the magnetic dipole moment. And so I had you skip down then to chapter 4, God bless, the beginning of chapter 4, where he takes the approximation from the exact answer in chapter 3, where he demonstrates that the A field, the far field behavior of A from this magnetic dipole, from this current loop, looks just like that. And again, the magnitude of A goes like r to the minus 2, just like phi does, but now A is a vector potential and it has a direction associated with it. And you can sketch A for yourself. Remember, A is in the direction of the nearest current, tends to be in the direction of the nearest current. Of course, there's possibly some cancellation, but you could sketch A for this pretty easily. And then B, you can obtain by taking the curl of A, which takes a little bit of work, but after you do that, and after simplifying some, you find that it has a very interesting form. Let's see, which is very reminiscent of the E field. fact, it looks mathematically the same, substituting M for P. So we have this magnetic dipole moment. We can increase it by increasing the current or the area of the loop. Okay, so the magnetic dipole field looks just like the one I sketched here. That's the sketch would be the same. And that would be the far field around a natural magnet. You get far enough away. Again, R has to be much larger than the size of the magnet. So in this case, it would be much larger than the radius of the loop. And then you would have the magnetic field would look like that. Okay, so any questions about that? That's half of the homework. Interesting to see the parallel and the similarities and the differences between these things. Okay, now, so I'm going to ask you a question. Suppose we have a field that looks like this. Let's suppose we have an electric field, and I put a charged particle somewhere in that electric field. What will happen to it? Let's suppose it's a positive particle. So it'll follow the direction of the electric field. It'll gain impetus in the direction of the electric field. Of course, now as it moves, it's going to be gaining impetus, so it won't exactly follow the electric field line, but there will always be a force in the direction of that. And so if we put a particle over here, for example, it would tend to move downward and tend to be pulled back into the bottom of the dipole, because the bottom of the dipole is the negative charge, the negative half of the dipole. So a positive charge would get steered towards the negative side of the dipole. A negative charge, of course, would go in the opposite direction, tend to be steered towards the positive side of the dipole. Okay, and you could put it at rest. There's a force acting on it, which is Q times the electric field. So it'll give the charge impetus, and then once it starts moving, it's going to, of course, be directed by its impetus, but also the force will steer the impetus, tend to change the impetus. So it'll tend to pull it in towards the opposite end of the dipole. Okay. Okay, now what happens if we have a magnetic field like this and we put a charged particle in? Suppose that this is now the magnetic field around a current-carrying wire far away, or a natural magnet, and I put a charged particle at rest. What happens?
Nothing.
Nothing, right? As long as the field is remember, in the magnetostatic approximation, there's not going to be any force present on this thing. Okay, so if I have to give it some impetus, if I give it to make something interesting happen, if I give it some impetus, now what happens? Well, remember, you did the motion of a charged particle with impetus in the presence of a magnetic field. It goes in a circle if it has impetus perpendicular to the magnetic field. But there was no force if it has impetus parallel to the magnetic field. Remember, the force is V cross B. If the impetus is parallel to the magnetic field, there's no force on it. So there's only a force in the plane of perpendicular to the magnetic field, but parallel to the magnetic field, there won't be any change in the impetus. So in other words, what happens in that case, if I put a charged particle in, and this is now a magnetic field, if I put a charged particle and I give it impetus, now it will spiral. And suppose I'd given it some upward impetus. And in fact, it's a more advanced homework problem than we'll do here. If the field lines are curving slowly, then the charged particle will execute a helical path and will be steered along the field lines. So depending on whether I give it an upward or downward impetus, it'll go either towards the top or the bottom pole. A single charged particle will move in that direction. Okay. So of course that's what happens when charged particles from the sun encounter the magnetic field of the Earth. They get steered towards the polar regions and away from the equatorial regions, which is what produces the aurora. But I wonder if you have seen this before. That's an aurora on Jupiter, in the polar region of Jupiter. It looks like a Hubble picture, judging from the thing down here. I don't remember where I got it from, but here's a surprise. here's an aurora around Ganymede, which is a moon of Jupiter. Which means, of course, two things. There's a magnetic field. Ganymede has a magnetic field. And the other thing is that Ganymede has an atmosphere, because these charged particles, when they hit the atmosphere, will cause the light and light up the atmosphere. I thought that was pretty neat. Okay, so now there's also an electric field near the Earth's surface. I mean, there's obviously a magnetic field. And the origin of the magnetic field, I guess I'm not really sure about. What is the mechanism of the origin of the Earth's magnetic field? I need to go read up on that. I've once learned about it, and I've forgotten. No. There is an electric field near the surface of the Earth, but it is not aligned with the poles, unlike the magnetic field. There is an electric field which has to do with the distribution of charge near the surface of the Earth, and is pointed either up or down all the way around the surface of the Earth. So it's not oriented to the poles, and it has more to do with the generation of charge in the atmosphere and things like that. So, but it's not particularly strong, but it is measurable. You can measure the electric field near the surface of the Earth. Okay, now let's suppose we go next. Let's suppose we put a dipole in a field. So let's see what happens to a dipole. Now we've sketched what the fields look like around dipoles, but let's suppose we take a dipole and we put it into a field. And let's start off with a uniform field. So let's take an electric dipole and put it into a uniform electric field. And remember, the way we can do that is by generating a uniform electric field by a parallel plate capacitor. So we start off by putting charges uniformly distributed, equal amount on the top and bottom of these two plates, put them in parallel, and remember, we want the separation between the plates to be much less than the size of the plate. So I have to continue drawing this out here in order for there to be a really nice uniform electric field. And the electric field, of course, in this case will be pointed downward, right? It's going to in the direction in which the positive charges will move. They'll move towards the negative plate. So if we were to put a dipole in this field, what would happen to it? And that's the other part of the homework. Let's suppose we put a dipole like this, and here's the dipole, the vector that separates them from the negative charge to the positive charge, and the dipole moment looks as QD again, like that. Now you can see quite easily without just by reminding yourself of how the electric field is generated, it's very easy to see what will happen to this dipole, right? The positive charge is going to be repelled by the top plate, and the negative charge is going to be attracted by the top plate. And so this dipole is going to want to flip so that the positive end ends up down towards the negative plate, and the negative end ends up towards the positive plate. But we can be a little bit more specific about that. One is to note that because we have the electric field here, the force on this positive end is going to be that way, and the force on the negative end is that way. And they're going to be of equal magnitude, just opposite directions. So the net force on the dipole is 0. There's no net force on the dipole. That is, there's an equal force on both directions. So the dipole is not, if you put the dipole at rest, it's not going to, the center of mass is not going to be accelerating. It'll stay where you put it. But there is definitely a torque on the dipole. You can see that torque is going to try to torque it over. So if you calculate the torque, the easy way to calculate the torque here, calculate the torque on the positive end, and we're going to calculate it about the center of mass. And of course this vector here, which is the radius to the positive charge, is d over 2. So it's going to be r cross f, right? So d over 2. And the force is going to be QE. I'm going to pull the Q out here. So that's the torque on the positive end, and the torque on the negative end is opposite charge, but also the D vector is in the opposite direction. The R vector is in the opposite direction. So there is a net torque, which is the sum of these two, which can be, then you can add them together and you get P cross E is the net torque on this thing. So if there's going to be, clearly then, if P is perpendicular to E, there's a torque that's going to, and that's going to move in the direction we just said. It's going to pull the positive in towards the negative plate. And you can also see this express the same tendency by looking at the total potential energy. Remember, we can define a potential energy as F dot delta X only if, or delta R, only if, what's the condition on F? That we can say that the change in potential energy due to a displacement is F dot displacement. Say again? Yeah, more than a conservative force. More specific. It would be a conservative force, the change in potential energy, I should be negative here, would be negative F dot dl along a path. But I can write it F dot delta R only if it's a constant force. Constant force is always conservative if it's uniform everywhere. So, and in this case, the force is constant, right? I can put the charges anywhere because the electric field is the same everywhere. It's uniform. So I can write the potential energy this way. Okay, so then I can write the total potential energy. Turns out to be negative QD dot E or negative P dot E. And that says that the dipole wants to have the lowest potential energy. It's going to move in that direction. If it starts from rest, it's going to move in that direction. And that's going to try to align the dipole with the electric field. So the dipole is going to try to, in a uniform electric field, it's going to act like a compass. It's going to rotate until it points in the direction of the electric field. Well, this is an electric dipole. It's not a magnetic dipole, but it does the same thing as a magnetic dipole. The magnetic dipole wants to rotate so that the magnetic dipole moment is in the direction of the magnetic field. Okay, now you don't really have enough to derive these same expressions, but you can go through the same sort of argument to show that these are reasonable. And the easiest way to do that, there are a couple of ways to do that, but I'm going to I give it a second way in the homework, but I'm going to just talk about this one right now. Let's suppose we have a solenoid. That would be the way of generating a uniform magnetic field. I want to put a magnetic dipole in this magnetic field, right? And in the middle of this solenoid, there's going to be a uniform magnetic field pointing in which direction? Upward, right? So there's inside of this cylinder, there's a uniform magnetic field. If we get outside, we get fringing fields and all that stuff. So let's just look inside. In fact, if you get far away from the solenoid, it looks like a magnetic dipole, right? It would have a fringing field if you get far away from it. But inside the cylinder there, up close, inside the cylinder, it has a uniform magnetic field pointing up. Now let's put a magnetic dipole in there. And I'm not going to use a natural magnet because, again, we have less understanding of how a natural magnet works, but I'm going to replace it by the analog of a current-carrying loop again. And let's look down on that. Here's the magnetic field. And so I have uniform magnetic field everywhere. I'm going to put a current-carrying loop in there, okay? And the way to remember that is here's the current flowing in the solenoid. So if I put my little current-carrying loop inside that, and I put let's suppose I put the current, here's the current in the solenoid and the current in the loop. What's going to have a lower energy arrangement if the current in the loop is in the same direction or is in the opposite direction? Remember our Ampere's force law between current-carrying wires. When they're straight, what attracts and what repels? Like impeti attract and opposites repel. So this would be lower in energy. It would be more attractive than if the current in the loop is flowing in the opposite direction. Okay, and you can go through a little bit of an argument. So what if the loop is at some funny angle? And it's not just at that angle. It's either this way or this way. What if it's at some funny angle? And I go through that in the homework. And you don't really prove it, but you can see at least that it's reasonable that the total energy, well, first that there's no net force on the loop, and then that the total energy is minus m dot b. That's consistent with what we just kind of sketched, and the total potential energy, and that there's a torque on the loop, which is m cross b. which is very much analogous to an electric dipole in an electric field, uniform electric field. Okay, so there's a lot of parallel here. Even though the electric and magnetic fields are so different from each other, there are times when there's a lot of similarities, correspondence between them. Okay, now let's consider another situation. Let's suppose I have a long line with charge on it, and this generates an electric field that points radially outward. And how does the electric field depend on distance? 1 over r. So it's not a uniform electric field, right? This does not generate a uniform electric field. It's falling off as you get farther, like 1 over the distance from the line. How would I do that? How would I make something like this? Very simple, practical way of making a line that has charge on it. Really simple. I did this at the beginning of the term. Say conduction? Induction. Exactly how?
Getting a static charge.
Yeah, and how would I do that? How would I induce a static charge on this thing?
Rubbing against something.
Yeah, let's take. And what would I make this line out of? I don't want it to. I don't want the charges to run around, so I don't want a conductor. Right. Yeah. Plastic. Yeah. Rub it with rabbit fur or something like that. And you can charge it up like that. Okay. And now let's suppose I took a drop of water. This thing. There's an electric field. Now the water is a funny material. It's a funny substance. Its reaction to this can be understood as though the water is composed of tiny dipoles, as though it were a group of dipoles instead of being a single substance. But its behavior is similar to what happens under this circumstance. What we're studying here is though it were a bunch of little dipoles. So what are the dipoles going to do? They're going to align along the direction of the electric field, right? And which way is it going to be? The positive ends are going to be up, and the negative ends are going to be down. So the water is going to polarize, with the negative charges closer than the positive charges. Water does that. It's a very polarizable substance. Put it in an electric field, and it will generate. The electric field will generate in the water a dipole in response to the electric field. But now this is not a dipole in a uniform electric field. It's not uniform anymore, right? This is not a uniform electric field. So the force on the top is not going to be the same as the force on the bottom. Which one's going to be stronger?
Force on the bottom.
The force on the bottom is stronger because it's closer. So there's now a net force on this dipole. In which direction?
Towards the line.
Towards the line. There's going to be a net force on this in this direction. And the same is true if the water droplet is below, the force is up, right? What if I had charged the line negatively?
It would polarize in the opposite way.
Get polarization in the opposite direction, but what about the net force?
It would be the same.
It's still attractive. Okay, so that's evidence that what is happening here is not the same kind of electrostatic attraction that you have between opposite charges. Because I could charge the line either positive or negative, and it attracts the water. So it's not like the water has some charge on it, and then I charge up the line and I attract it because they have opposite charges. That's not what's happening. What's happening here is that the charge on the line is inducing a dipole in the water, and it then always has an attractive interaction. So I could charge up this line with the opposite charge, and it would attract the water. Yes, sir, Mr. Coulter.
Would that be similar to how water reacts to like a magnet? So in the presence of a magnet, it will actually dip down a little away from it. It's not exactly visible.
No, it's not going to be quite the same. I got to think about that one. I was actually unaware of that. I'd like to see that.
It's like a little thing. If you have like a Cheerio in a bowl of water,
Yeah.
you put a magnet over it. The Cheerio seems to follow the magnet. The Cheerio isn't magnetic. The water is just creating a little dip, and the Cheerio is falling into it.
Is that milk or water?
Water.
Water. Okay. I like milk on my Cheerios. No, I'd like to see more about that. Can you find that for me? I'd like to. I didn't know that. You're saying that the water actually dips under a magnet.
I mean, it's very slight. If you look at it from an angle, you can kind of see it.
Yeah.
Yeah.
I don't think that's the same.
Okay.
But I'd like to investigate that more. I don't know about that. Okay, but I do have here something that's kind of interesting. I want to show you then here. This guy drives me nuts here. How do I? Well,
On the left side, you think it's a marker and not an arrow?
yeah, but in spite of that, it still won't.
It's not that easy.
Oh, it does. Okay, all right. Now this guy drives me nuts.
And what you're
Here,
looking
you'll
at is a
you'll
knitting
see
needle.
why here in a minute.
And I happen to have in my a couple of knitting needles. And not that we have a lot of time to do knitting up here, but there's some other neat things you could do with them.
Knit.
And so watch
There's no
this.
G on the end of knitting.
So here I have a piece of paper,
Drives me nuts.
and I rub the knitting needle
Oh.
with a piece of paper.
He's going to do it the whole 3
This knitting
minutes.
needle is a polyethylene knitting needle. It's 8 millimeters in diameter.
See, you got you too.
And now I'm going to take a syringe with a little Teflon nut.
Okay, so he charged up the needle, right? And now he's going to, this is up in the space station.
Cannula. I'm going to squirt drops of water out, and look what happens when those drops of water get close to that charged knitting needle.
I wonder where he's from.
So this is like a little satellite going around a cylindrical shaped planet. Except the physics here is a little bit different. It's not about gravitation. It's about charge forces. And of course, charges can exert a potential field, as we call it. So it can exert a force at a distance with no tangible connection. And so you have a charged drop that was ejected from the Teflon tipped syringe. And then you have the charged knitting.
So, you remember when we did planetary motion, we considered the force required to keep a body in circular motion. So you could do the same thing here, of course, but the force is dropping off like 1 over the distance. No, that's not, yeah, the force is, but yeah, this is, yeah, I think that's still correct. So it's a dipole in this non-uniform field. So I gotta think about that. It's actually not correct. What I just said is not correct. So we have to, but anyway, we could figure out here the motion of this body around the knitting needle.
And they're going to be attracted if they're opposite charges. But because the drop has some velocity to it, it's orbiting around the knitting needle.
Okay, but I think he's wrong about what he just said. He said that they're opposite charge. I think he's implying that the water droplets actually have charge, right? But you could, if you took a knitting needle with the opposite charge, then as this from this one, then they would be repelled. But I'm guessing you would get exactly the same result, and that's because this is an example of polarization. This is the water being polarized by the charge on the needle.
Now this knitting needle happens to be a little different than when we started out. This knitting needle is made out of Teflon. And Teflon has some really neat static charging properties when you rub it. And I figured it'd be good to have a Teflon knitting needle when you're on station.
Okay. Okay, so when you get a chance to go up there, you know, please take your knitting needle with you. Okay. All right, so. Okay, now the last part I want to talk about is, let's suppose we have dipoles with dipoles. Let's put a dipole next to a dipole. What's going to happen? Remember, we sketched the field already, so you should already have some feeling for it. The dipole, of course, is going to want to be aligned with the electric field. That's going to be the lowest energy configuration. So if we skip back to our sketch of the field, electric field up here, and then let's consider what happens if we put a dipole in different places here. An electric dipole in the field generated by another electric dipole. Okay, so let's consider what would happen in that case. Okay. Okay, so one way to see that easily, you can go through the mathematics that we've just done to get a more precise answer. But suppose we put two electrostatic dipoles parallel to each other and stacked up like that along a line. Or compared to a situation where we take the two dipoles side by side. So we want to consider stacked configuration or side by side. Okay, which one is going to be more favorable? Which is going to be lower in energy if the distances are the same? The stacked, yeah, because we have the opposite ends are closer to each other. That is, the positive end on the lower dipole is close to the negative end on the upper dipole. That's going to be lower in energy than the side by side. What if they were opposite dipoles? If the dipoles were in opposite directions? Of course, then we'd have the opposite result, right? Side by side is better if the dipoles are opposite, and that's because the field points in the opposite direction. Remember, in the case where they're stacked up like that, the electric field is pointing upward, whereas side by side the electric field is pointing downward, and so that's why they want to form. So they want to form opposite orientation if they're side by side. Okay, so I'm going to put that into a table, which we're going to make use of in Chapter 4. So we have stacked or side by side, and this is parallel or anti-parallel. So if they're parallel and stacked, then this is attractive. They're attracted to each other. And also, if they're side by side and anti-parallel, they're attractive. But the other two arrangements are repulsive. Now, the same would be true if these were magnetic dipoles. And you know this probably from playing with magnets. If we put magnetic dipoles like this, then I have in the upper left configuration where they're stacked and they're in the same direction. The south pole of one magnet is closer to the north pole of the other magnet, so that's attractive. Whereas if they're like this, then the north poles are closer together and the south poles are closer together, and that's repulsive. It will push them apart. And the other way, if I stack them like this, the north poles are going to be together. That will be obviously repulsive. If they're side by side, they want to be opposites to each other. And so, okay, so that table I want you to remember. We're going to make use of this within a day or two. We're going to study induction, and we're going to find some interesting applications for the understanding of some interesting effects will be much clearer if you look at how dipole interactions go. So this is a pair of dipoles put in the vicinity, one in the vicinity of the other one. And so we're going to come back and remember this table. Okay, any questions about dipoles? It's kind of neat to see it all in one place. That's one thing. Maybe there should be some homework. I'm going to suggest homework for the next edition of the E&M text. Some homework like this or something where you can see the dipoles. Spend a little more time in it than it's a little bit scattered in the textbook. So I kind of like it in one place. Mr. Dowell.
So going back to the A and B fields for
Yes.
the solenoid.
Yeah.
So can you explain the direction vector for the area?
Yes, right. So you have a magnetic loop, and it's by convention, right? These areas can have one of two different directions associated with it. That would be an easy thing to do. Let's see here. I guess I have to go back. Where is it? Okay, where did I put it? Well, okay, I understand your question anyway. The idea was to here if we have a little loop carrying current, then I define the area vector such that if you're looking down on that, the current is flowing clockwise, counterclockwise. So that's the convention for choosing the area in a case like this. We had, of course, when we were doing Gaussian surfaces, we had a completely enclosed volume, and then we could choose the area to point outward, and that was very unambiguous, right? There's an inside and an outside, point the area out from the volume. In this case, it's ambiguous whether it should point up or down. We choose it such that when you're looking down on it, that the current is flowing counterclockwise.
Okay, and that's the total area inside the.
Yeah, A is then points in the direction that I just described. Yeah. So it's normal to it and pointing such that the current flows counterclockwise, and then the magnitude is the area of the loop.
Okay.
So up means such that the current flows counterclockwise.
Yeah.
Okay, so let's see here. God bless. Hello, come on. We have a new VGA cable. Nice, robust thing, but it's not connecting. Yeah, robust. Oops. All right. Come on, there we go. Okay. Now let's see if I can get this thing to go to a reasonable size. Okay. All right, so this is a kind of roadmap of partly where we've been and where we're going. So we've covered chapters 2 and 3 so far, electrostatics and magnetostatics. We're going on to chapters 4 and 5 next. And I want you to see the logical progression of this because it really does make a lot of sense the way he's structured this. So remember the condition for the electrostatics in chapter 2 was we put charge in place and don't let them move. So no currents. And then we looked at the electric field, and we found that the curl of the electric field is 0, and the divergence is caused by a charge distribution. Then we looked in chapter 3 at magnetostatics, and in that case we had to have stationary current loops. You don't want the loops moving, and you don't want the current flowing. You want those loops to be complete loops, so there's no gaps, so there's no charge building up anywhere. And you also want the current in those loops to be constant in time, don't change in time. So that's the magnetostatics condition. Okay, now we're going to gradually relax these restrictions until we get to a fully dynamical understanding of the electromagnetic field, which is fascinating. It's very interesting how these things are connected to each other. And the first thing we're going to do in chapter 4 is study magnetic induction. And so we're going to partly relax the conditions of magnetostatics. And one thing we're going to allow is for loops, now the wires can move. Or we'll allow the current in the loops to change in time. We're going to do both of those things in combination in chapter 4. In chapter 5, we're going to relax the condition that the current has to circulate. There can't be any charge buildup anywhere. We're going to relax that condition in chapter 5. So that when we get to chapter 6, we'll relax all of those conditions. We'll be able to handle anything. We can let them move around and do whatever they're going to do, as long as charge is conserved. That is, so that if you have current flowing into a region, that's charge building up. That will be the only condition left. Okay, and in all of these chapters 3 through 5, we have the instantaneous propagation. That is, the distances involved are short enough and the times long enough that we're not worried about the time it takes for the change to propagate through the plana. We're saying that it's instantaneous. If I change something here, it immediately results in a change in the field over here. I'm not worried about the time it takes for that to propagate. So the speed of light is so fast under these conditions that I don't need to take the delay into account. Okay, and that's going to be true all the way through 5. When we get to 6, we'll relax that. We'll give that one up. Everything's going to be fair game. Okay, so now let's consider what's going on in chapter 4, excuse me. We're about to start on chapter 4. You have some homework for chapter 4 to get you started for Friday. So we're going to find that current flowing in one loop can induce current in another. conductor under certain conditions. Okay, and remember that current is a shorthand word here. By current, specifically, remember, we mean a body with charge and impetus. And it could be, has parts virtually that have impetus, charged parts with impetus. So we're going to talk about currents. So let's suppose we have two loops. And they don't have to be square, but I just drew them as square. And we have current flowing in the left loop. I'm going to call that the primary. That's the one that starts off with current in it. So there are charged parts inside that are moving. And the wire loops themselves are electrically neutral. That is, they have just as many positive as negative charges. So there's no net charge on this thing. And then I have another loop next to it that has no current in it. And if I just do that, and leave them there, nothing happens. Nothing more happens in the sense that the secondary, there's no current flowing in the secondary. As long as I just leave it like that, this is the way it will remain. Okay, but if I move, there are three different things you could do. You could move the secondary towards the primary. You could move the primary towards the secondary, or you could change the current in the primary. Those three different things. All of those will induce a current in the secondary, but for different reasons. And I want you to, and part of understanding magnetic induction is to understand how this happens. Okay, so remember the three things I said. Move the secondary towards the primary, or away. Move the secondary. Move the primary, or change the current in the primary. Any of those three things will cause current in the secondary. So let's suppose we push the secondary towards the primary. A current will flow in the secondary such that, in this case, if the current flowing in the primary is counterclockwise, the current flowing in the secondary will be counterclockwise. The second phenomenon is I'm going to move the primary towards the secondary, and I get the same end result in that the secondary has, insofar as we're talking about the current in the secondary, I get current in the secondary flowing in that same way, counterclockwise. The third way is to increase the current in the primary. I can decrease it, but if I increase the current in the primary, I'll get, again, counterclockwise current flow in the secondary. So these three things all introduce counterclockwise flow in the secondary. If I push the secondary towards the primary, if I push the primary towards the secondary, or if I increase the current. All three of those things induce current in the secondary. But that all of those require some change. You have to change the place of the secondary, or change the place of the primary, or change the current. Something's got to change. If you just left them like that, like this, nothing would happen. Right? Got to have some change. And remember, we could get current to flow before by putting a battery in it, causing an electric field inside the conductor. So there's a connection here between cause of a current and the magnetic field, right? We have magnetic field outside of the primary. So something's going on relating, interconnecting current, which we thought of in terms of electric fields, and magnetic fields, which are generated by the primary. So there's an interconnection between these things now that we hadn't discovered before. So there's three phenomena and two causes. And we'll talk about, let's see here. Yeah, okay. So when I move the secondary towards the primary, that's caused by a V cross B force. And we'll explain this here in just a second, how that works. But the other two cases are actually the same cause, and that's called the A dot effect, and we'll explain what we mean by the A dot effect. It's a change in A, the vector potential, is causing the induced current, whereas in the first place, it's what's called the Lorentz force. It's a V cross B force. So let's look at the first case. We have a primary that has current flowing in it. That causes a magnetic field at the secondary that's into the page here, right? Magnetic field circulates around the wire in that direction. And now we're going to push the secondary towards the primary. And if the current, the charge carriers in the primary are positive, now we're moving those carriers, those mobile carriers, in the presence of a magnetic field. And that produces a V cross B force. Q V cross B is, in this case, downward. Right? V cross B is downward. And so that's going to push those, it's going to, that's the problem with doing it this way in one view graph with these transitions. It's going to push the charges downward. That's going to induce current flowing in the counterclockwise direction. That's the first method for inducing a current, and I think I better let you go now. You're going to read about these three effects and how they're related to each other, but they're actually fundamentally two different causes going on. And because we need to sort out cause and effect, we need to understand exactly how this is happening. And so he's going to walk you through it so you really understand magnetic induction very well. And to really understand magnetic induction, you need to understand the effect of the vector potential. The vector potential now, remember we said it was a potential momentum. And now the role of the vector potential is going to become clear now. You'll understand it much better because we'll see its role in induction. Okay, so we'll see you on Friday. Yes, sir, Mr. Miller. Go back a slide.
Yes. To the chart.
Oh, to the chart?
Yeah. Thank you.
Yeah.